please start.
Okay, sir. So the title of this the paper was quantum simulation on digital computers. So first of all, we will see the motivation behind the quantum simulation that has been described in this paper. So why quantum simulation? So this idea goes back to Feynman's lecture in 1982, where he proposed this idea that if we want to understand the nature better, as nature is not classical, so we have to understand it on kind of devices which work on the laws of quantum physics. So he gave this idea of quantum simulators. Now, why we want to do the quantum simulation? Because it has lots of applications, like it can help us in information processing tasks. It can do wonders in computation, sensing, communication, and metrology. So it can help in the weather forecasting and climate change, global warming, and it can be also useful in efficient and energy storage devices that we can it can help us in building such energy storage devices. It can help us in drug development, for example, those medicines which are currently not possible to make. For example, we have Alzheimer's disease or other diseases which is very hard to understand because of the protein folding, and we can simulate that protein folding with the help of quantum computers and other such diseases. And when we better understand them, we can make such medicines to cure them. We can also make fertilizers, and thus it can help us in reducing carbon dioxide emission. There is a greater amount of carbon dioxide emission that is coming from making the fertilizers. So quantum computers can help us in, it is being said that it can help us in making those fertilizers, which will not contribute much to the carbon dioxide emission. And it is very useful in quantum chemistry. It can help us in simulating or understanding the complex molecules which are currently not possible from the what we call as the classical or conventional computers. And also it can help us in discovering certain new materials like high temperature superconductors, which are currently not possible, and they can help us in transmitting power over a larger distance without losing much to the environment. And also it can help us in improvement of certain mathematical algorithms. Now, what is quantum simulation? I mean, if we want to give the definition of quantum simulation, how we will define it. So we define it like it uses some quantum principles like like superposition principle and quantum entanglement to construct a physical models that can mimic or copy exactly the original system, and can help us understand real systems. So this is the simple definition about it. It simply uses quantum principles to understand the real system. Then how do we do it? I mean, the quantum simulations. So there are three ways that we can do this. We have analog simulators and digital simulators and quantum annihilators. And large big industries are working in building these simulators, but the simulators that have been discussed in this paper is digital simulators. So we will only focus on digital simulators, about their hardware, software. Basically what they do, they're using platforms that use large arrays of single quantum systems. They can be atoms or ions to solve complex systems. So that's how they do it. And we will see what does it mean using those platforms of atoms or ions to solve complex systems in coming slides. So then in this paper, it has been discussed what is available technology to us in hardware side and software side. So first of all, we will see hardware side. So there are three properties that we are looking for while building the hardware system. So those three characteristics that define a good hardware are: number one is long coherence time. Coherence time means that the amount of time for which a qubit can store the information in it. And we always want that this coherence time should be much larger. much larger it is, the better will be the results. So second is fast gate operation speeds. We want our gates should be very fast. And number third is high gate fidelities. I mean, fidelity, we mean that we want to reduce the errors. We want they should be very much accurate. So these are the three characteristics. So then there are certain technologies that have been employed since decades by certain big industries. Like we have a technique called superconducting qubits. This is being utilized by IBM, Rigetti, and Google. And there is another technique that's trapped ion qubits, which is being used by Honeywell, and another one is photonic qubits, which is being used by this big industry called Xanadu. So first of all, we will see what are the superconducting qubits, which is being used by industries like IBM and Google. So basically, superconducting qubits are solid state circuits which contain Josephson junction, LC oscillator, and we can build different kinds of qubits out of those if we change the capacitance and inductance. Like we have phase qubits, flux qubits, charge qubits, and so on. Now, they have this property that their coherence time is much higher, that is 50 to 100 microseconds. Their gate speed is of the order of 10 of nanoseconds, and their gate fidelity, the accuracies are almost that's up to 99.5% for 2-qubit system. Then there is another one, it's called trapped ion qubits. So it is being used by Honeywell. What they do in this trapped ion qubits, as the name suggests, they trap the ions in late straps formed by electromagnetic fields. They serve as a qubits. We have an ion which has a net positive or negative charge, and the last, either they are deficient of an electron or they have an extra electron, then that acts as a qubit. They store the information, they manipulate this last electron and make this as a qubit. And these internal electronic states of the ions, they are mapped to the qubit states. And when we see their coherence time, that is much higher than the superconducting qubits. So they win on this side, that they have coherence time is much higher than the superconducting qubits of that is greater than 10 minutes. But from this side they win, but on another side they lost. Like this gate speed is not much higher, that is very slower. I mean, that is 2 times slower than the superconducting qubits, but their gate fidelity is good, that is 99.99% for 1-qubit system, and also 99.9% for 2-qubit system. Then there are some technologies which are emerging right now, and lots of work is being done around the globe. It's called based on cold neutral atoms. So this is based on this cold neutral atoms arranged in a lates using optical or magnetic traps. So then they use their properties like Z-man or hyperfine ground states, and they store the information, or they use them as qubit states. Then there's another one which is being right now hugely investigated. It is called the topological qubits. They have very good property that they are very insensitive to environmental noise. See, the other techniques that we just discussed, they are not insensitive to the environmental noise. When we try to manufacture the hardwares, there comes this environmental noise, and that is not good for us, and we want to reduce this noise as much as possible. Then there comes this topological qubits, which are very insensitive to environmental noise, but they have not been yet practically implemented. It's very hard right now, and work is being done currently. And because these topological qubits, they are actually quasi particles. That means they are neither bosons nor fermions, but they obey anionic statistics, and they are also called Majorana zero modes, and it's being investigated currently. Then from the software side, apart from the hardware, we need also software. So basically it is needed to design the quantum circuit that carries out material simulations, such as we have to prepare the initial state, we have to see how the Hamiltonian evolution happens, and finally we have to also measure the desired observables. For that we need software. Now, there are certain algorithms for material simulations, but there is very a small number of quantum algorithms right now, because they need a very huge substantial quantum resources like a large number of qubits or deep quantum circuit, which is a very hard task right now, because as we try to increase the qubits, there comes this errors, and it becomes hard to simulate any kind of problem. And also work is being currently done in this area also, which is called quantum error correction. It's a very large field where we try to reduce the errors. So that is one obstacle that prevents us from constructing much more quantum algorithms. Because if we want to make or produce good algorithms, for that we need a large number of qubits, and doing large number of qubits, it is very hard right now because of noise. Then we have certain software packages which has been developed by these big companies like Microsoft. Their software package, it is called Quantum Development Kit. Simply, and there is this Google Open Formula, and IBM has this Qiskit, and others have their own. And they can solve lots of problems like ground state energy computations, excited states, dipole moments, and others. And there are certain algorithms like we have VQE, variational quantum eigensolver, and QPE, quantum phase estimation. We will try to understand them in later slides. So first of all, what we need to do while we do the quantum simulations of some materials, first of all is we have to do the state preparation. So this is central to material simulations on quantum computers, that we have to prepare a wave function which is called target wave function. First of all, it is represented as psi of t. And once we do it, so how do we do this? How do we prepare the target wave function? So we take some fiducial initial state size 0, and then we apply this unitary operator on this, which will help us in seeing the dynamics of the system. Once we apply this on this initial state, it will lead to some final state psi f cat. So once we apply this unitary operator, and we expect that it should follow this relation, that 1 minus inner product of psi f psi t, and that there comes this error, and that should be very less than or equal to this some algorithmic error e. So it should follow this relation. So once we are done with this, I mean, we prepare the target state, and then we can measure the information in static material simulations. So static material simulation is not that much hard as compared to dynamic simulations. Once we prepare the target state, and we can measure it. But in dynamic simulations, we have to also see the dynamics of it, and that how the Hamiltonian evolves with time. So that is a major task for us. Why we want to initialize into some ground state is because ground state is the most stable state, and it can provide us lots of information about the system. So basically, there are certain methods by which we can initialize the system into the ground state of some Hamiltonian. So like we have the method QPE, it's called quantum phase estimation algorithm, which can be used to find the phase theta of an eigenvalue of a unitary matrix U, which is applying on this psi ket. It gives us the eigenvalue e to the power 2 pi I theta. So basically, once we try to understand to calculate the ground state energy, basically we are trying to find the lowest possible eigenvalue, and that eigenvalue is given by this e to the power 2 pi I theta. And this theta, it represents the phase of this eigenvalue. To calculate this phase, it is a task for us, so that that theta can be calculated by this algorithm. It's called quantum phase estimation. So once we apply this unitary operator on this, which is equal to e to the power minus IHT, and H is here Hamiltonian, and we can find the eigenvalue corresponding to it. So this is a quantum phase estimation is generally used to find the ground state energy of a material, which is basically nothing but the smallest eigenvalue of a material's Hamiltonian. So that's our task basically in it. Then there is another one, it's called variational quantum eigensolver. It is one of the major algorithm in quantum machine learning. Why? Because it is very important. It helps also helps us to find the ground state energy, and it has been implemented by IBM, Google, big major industries, where they were simulating, or they were trying to calculate the ground state energy of certain materials like lithium hydride, beryllium hydride. So this is the method, one of the method that is used to calculate the ground state energy. So basically, it is nothing but a hybrid quantum classical algorithm. It uses both quantum as well as classical computers to calculate the ground state energy. So class quantum computer, it simply makes our wave function, or what is called in quantum computation NSATs. NSATs is basically our the architecture of the circuit that's being produced by this quantum computer, and classical computer does the job for setting some parameters, what is called as variational parameters, and that is being done by the classical computer. Now, why we do this, why we need here classical computer if we are doing the quantum simulation? um, because this job setting the variational parameters, that can be done on the classical computer as well. So why we need to make our quantum system more complex? For that, which that job can be done on classical computer. So that's why we use the classical computer also in this while implementing this algorithm. So quantum computer is used to construct the wave function, while a classical computer is used to optimize these parameters to minimize the expectation value of the Hamiltonian. Basically, all we are trying to find is the expectation value of the Hamiltonian. So the steps that are required to implement this step is, first of all, we start with a random set of parameters. This job is being done by the classical computer. So it works on the called variational principle in quantum mechanics, where our wave function is dependent on some parameters which are called variational parameters, like we have here theta. So this is being set by the classical. Then what we do once we prepare the trial wave function, we would be interested in measuring the expectation value of this Hamiltonian for this particular wave function. Once we what we want, actually we want to calculate the minimum possible energy, I mean the ground state energy. So once we do this, we again send this information back to the classical computer, and that sets a new set of parameters, basically, that tries to minimize the energy. So that can be done on the classical computer. That's why we are sending it back to the classical computer, and that sets a new set of parameters, and we send again back to the quantum computer, and this repeats until the convergence in energy is achieved. What does that mean, convergence? Because we want to find the minimum possible energy, that is the ground state energy. And once we match the energy, once we get the convergence in energy, then at that point this circuit, we expect that circuit should prepare the ground state, or the state very close to the ground state of the Hamiltonian. So this is how this variational quantum eigensolver works, and it requires a smaller number of gates because we are using the classical computer. So our circuit will not be much more complex, and it requires shorter coherence times than quantum phase estimation. And it okay, so this was about the preparation of the ground state energy. Now there is this Hamiltonian evolution, which is very important if we want to understand the dynamic simulations on quantum computers. So what we do in the Hamiltonian evolution, first of all, we know that time evolution in quantum mechanics is given by this operator, e to the power minus ist, where h is this Hamiltonian and t is the time. So this is given by this Taylor series, 1 minus ist minus h squared t squared 2 factorial plus so on, so on. We want to understand this, but it is not so much easy to simulate this or to understand the evolution of this Hamiltonian, because this Hamiltonian, it is a Hermitian matrix and it is exponentially large. So it has some known structures that allows us to efficiently compute Hij, where Hij is the component of this big Hamiltonian H. Now, what does this mean, the known structures? That will be much clear in the next slides. So basically, let's first understand what is our goal in quantum simulation. So our goal in quantum simulation is to compile this unitary evolution into a polynomial sized gate sequence. What does that mean? So here you can see this is the physical system, our original physical system that we want to simulate. and this is our quantum computer on which we are doing the simulation. So what do we mean by quantum simulator? That is, we mimic the properties, we mimic its all properties on some system, what is called as quantum system, and so that it is controllable, we can control it. But this physical system, we cannot control it because it's very much complex, and we do not have that much of advanced technology that we can play with this physical system. Now, this is the original wave function in this physical system, psi 0, and it evolves with time under this unitary evolution operator e to the power minus ist to some another point. So this is its evolution. Now, how do we simulate it? How do we understand it is evolution on the quantum computer? We start from this point and we say that it evolves like this. It is just a random trajectory. It evolves like this. Then we divide this whole trajectory into sub parts by applying the gates. So this is one gate here, this is another gate, this is another gate, this is another, and simply. So basically this whole trajectory, it represents an Hamiltonian, and we break that down Hamiltonian into sub-Hamiltonian, into subparts. So you can see this by applying the gate operations. And how do we do after that? What we do after that, that will be clear in these slides. So our central challenge is to approximate this unitary operator where h is known, but u of t is not explicitly known. So once we break it, this Hamiltonian into sub-Hamiltonians, then we have certain kind of known structure of this sub-Hamiltonian. That means we know its form. What is its form? It may be in some form that we can simulate, that we can understand, but this whole Hamiltonian, it was not known to us. So what is the central strategy behind simulation is to reduce the problem to easy to compile sub problems. Basically, we want to break it into sub problems so that we can simulate it. So there are certain strategies for doing this, like we have Trotter-Suzuki formulas, which is very famous in this, and there are randomized evolutions, linear combination of unitaries, quantum walks. So these are the four broad strategies. First of all, we will try to see what is this Trotter-Suzuki formula, how it helps us in understanding this quantum simulation or the Hamiltonian evolution. So this is the Trotter-Suzuki simulation. The key idea in it is to break the simulation problem into a sequence of easy problems that we just saw on the picture. So how do we do that? For example, our Hamiltonian our original Hamiltonian was h, and we say that is the summation of these Hamiltonians, hj components, and there is this component coefficient multiplied to it. So we take the summation of those all Hamiltonians, which is equal to basically the net Hamiltonian h. So our unitary evolutionary operator will be equal to e to the power minus I, and in place of that h, we place this summation of aj, hj. These are the components of that Hamiltonian multiplied by time. So what is our intuition in this? We would be interested in simulating this Hamiltonian by this evolutionary operator by rapidly switching the terms on and off. What does that mean, on and off? For example, first of all, we have, I would go back to the previous slides. So here, for example, we have our problem was this whole Hamiltonian. Once you break it down into sub-Hamiltonians like this. So what we do, once we simulate this one particular Hamiltonians, this will be on, and these all Hamiltonians will be off by gate operations. Then this will be on, others will be off, then third will be on, and others will be off. So that's how we do this. We will do this so fast that it seems that all have happened at once. So I can show you this slide. Yeah, if we do this rapidly enough, it is as if all the terms are at once. So we do all these sub-Hamiltonians so fast, it will seem that it has happened at once. it will take very less time in doing that. So finally, our evolutionary operator, which was equal to e to the power minus iht, it would be equal to product of all those evolutionary operators, e to the power minus ih hj is a single component, hj t divided by r, and this whole power r plus this is the commutation relation hj hk, and this will basically give us the error, and that how much error we are getting in it. And this r, it represents the number of time steps. So greater the number of time steps, less will be our errors. And how do we apply this eigensolver, variational eigensolver? If we have the classical computer here, we have the quantum computer here, we encode some information in the quantum computer, we apply some certain initial wave function. Once we apply the initial wave function, we apply the unitary operator on it, we understand its evolution, then we send it back to the variation the quantum computer. What a quantum computer, this classical computer has to do, it has to set a set of parameters by variational change. So there is this principle in quantum mechanics called a variational principle, by which we can minimize the parameter. So for each iteration, we try to minimize those parameters. So first of all, we prepare this wave function psi of t, and this is t. This applies some transformation on it, and with respect to some reference wave function. Then we finally measure its energy. And for each iteration, this classical computer has to do the job that it has to lower down or minimize the energy of the eigenvalue and send it back to the quantum computer, so that it can again do the iteration. And this iteration will repeat till we get the convergence between the ground state energy and this minimum eigenvalue. And the example that is already told about this lithium hydride, it has been studied so far. And this dotted line, it represents the classical simulation, and this black dots, it represents the simulation that was done on the quantum computer. So there was very convergence that was found between the classical and the quantum computing.